So chapter 4, applications of derivatives, section 4.2, how derivatives affect the shape of a graph. We're going to finish this off. Good afternoon, everyone. Let's get this started. We are going to graph this function, f of x equals 1/2 x to the power of 4 minus x squared. And to do that, first I want to look at it from the point of view of algebra. And that means, first let me find the intercept by setting it equal to 0. When we do that, this gives us x equals 0. And of course, the multiplicity is 2. This gives us x squared equals 2. X is plus minus square root of 2. And therefore, the following intercepts. So if we were to graph this, here's 0, 0. Square root of 2 is about 1.41 roughly. So somewhere here, 1.410, negative 1.410. And this one has multiplicity 2. So we use double arrow, which means it's not going to cross as it hits it. When we look at this one, we know the degree is even and 1/2 is positive. So the end behavior looks like x squared, meaning the first and the second quadrant. So if we were to graph this, when we hit this x-intercept, we have to come back up at some point to hit the next x-intercept. It can't cross that because of the multiplicity event. Has to come back up at some point. It crosses the last x-intercept, and it looks something like this. But where is the function increasing, decreasing, stuff like that? We are going to use calculus. So we already have an idea how it looks like. But let's make it look better. So we want to go with the first derivative test, and we're going to use a sign graph. That means we have to come up with f prime of x, which is 1/2 times 4, 2x cubed minus 2x. We set this equal to 0 by factoring the 2x out. And it becomes 2x times 2 times x squared minus 1, which is 2x times x plus 1x minus 1. And we have 3 zeros, x equals 0, x equals negative 1, x equals positive 1. So we're going to do the sign graph. And we're going to put all these numbers in order from smallest to largest. So obviously from negative infinity to positive infinity, negative 1, 0, 1. Here's x, here's f prime. And what happens is we have to come up with TPs. But I want you to notice the exponent on this one and this one and this one, all of them are 1. Therefore, even if you find one of it, the rest of them will alternate. But the CP, the TP is short for test points. Over here, we would use minus 2, over here minus 1/2 in between, right? Positive 1/2, and let's say 2. For example, if you plug in 2 into f prime of x, 2 cubed is 8 times 2, 16 minus 4 makes it 12. It's positive here. And as I said, they will alternate. But you can check all of those test points and you'll see that it works out. Sometimes it's easier to evaluate it here. Sometimes maybe easier to evaluate it here. And let me throw in the arrows so it can be clear. Arrow down, arrow up, local mean, arrow up, down, local max, down and up, local max. So we have a local minimum and local maximum. The easiest one, of course, if you plug in 0 into the original function, gives you 0. So 0, 0 is the location of a max. But what about the minimum? You have to put these two numbers into the original function. And both of them result in the same thing because this has exponent even, this has exponent even. Negative or positive to the power of 4 makes no difference. Each one is 1. Therefore, this is 1/2 minus 1, which makes it negative 1/2. And we say local minimum is negative 1/2 at plus minus 1, meaning we have the following pairs: negative 1, comma negative 1/2, and positive 1, comma negative 1/2. As I said, local max is 0 because you plug in 0, you get 0. So local max is 0. Either you say at x equals 0 or 0, 0. Now, where is the function increasing? You see positive from negative 1 to 0, union 1 to infinity. Where is the function decreasing? Where we see negative. The function is decreasing from negative infinity to negative 1, union 0 to 1. So the first derivative test gives us local extrema, intervals of increasing, decreasing. We're going to move on to the next part, finding inflection points. So let's write everything that we got from the previous page. Here's the function. Here's f prime from the previous page. Here's the intercepts. This happened to be a local max. Here's the minimum. We have 2 points. Here's where the function is increasing. Here's where the function is decreasing. So this is everything we got from the previous page. Now we want to do the inflection points. So we have to differentiate again. So here's f prime. F double prime is 6x squared minus 2. To set this equal to 0, we're going to factor the 2 out. And to set this equal to 0, 3x squared equals 1. X squared is 1/3. So x is plus minus 1 over square root of 3 precisely. Let's do the sign graph. So possible inflection points would be at these 2 points. We set up a number line that goes from negative to positive infinity. We put these 2 numbers in order. Minus 1 over square root of 3 is first, 1 over square root of 3 is second. At this point, f double prime is 0, so is at this point. So test points, TPs, Of course, in between is 0. To the left of that would be -1, to the right would be 1. They will alternate because this has degree 2 and has 2 solutions. So 0 would be the easiest one. If you put it in here, 0 makes it positive. My apologies, positive 6 times 0 minus 2 makes it -2. So makes it negative. And they alternate, positive and positive. Or you can plug in -1, square it, +1 times 6, 6 minus 2, makes it +4 here. So positive, negative, positive. Which means what? These are the inflection points. The function is concave. This is negative. It's concave down here from -1 over square root of 3 to 1 over square root of 3. And it's concave up otherwise, meaning from -infinity to -1 over square root of 3 union 1 over square root of 3 to infinity. The IPs, we have to find the y coordinates. So we plug in these 2 points into the original function, f of x, evaluate them at those points. And by the way, positive and negative makes no difference because this has exponent even, this has exponent even. So first and foremost, please understand this: when you square it, you get 1/3. So when you square it, when you take it to the power of 4, that means 1/3 squared. So this becomes 1 over 9. This is basic math, everybody. So 1/2 times 1 over 9. This is 1 over 18 minus 1/3. 1 over 18 minus 6 over 18 makes it minus 5 over 18. So now we have the IPs located at plus minus 1 over square root of 3 and -5 over 18. Now, the reason I'm changing it to this approximation is for the sake of graphing everything. So we have all the information we need. We are going to graph all the points that we have. So first we're going to write the summary of the points. So we have a couple of x-intercepts at these 2 points. So square root of 2 is about 1.41. So this is 1.41 is about here, -1.41 is here. So we have one x-intercept here, one x-intercept here. Then we have another one at 0, 0, right at the origin. And we're going to put a double arrow because it is also a maximum, so the graph can't cross that. We have the IPs at these 2 pairs. So -0.6, let's say roughly -0.3. So here's -1, so -0.6 is here, 0.3 is here, so somewhere there, and +0.6, -0.3 is there. So those are the inflection points. Finally, the minimum at -1, -1/2, so this is -1. -1/2 is here, and the +1, -1/2 is here. And don't forget the double arrow for both cases because they are minimum. Again, reminding you that this has exponent even. This number is positive. We know the end behavior already, so it looks like that. Notice we have a local max, we have local mean, both of them are also absolute mean. The function is decreasing here, increasing here, decreasing here, increasing here, okay? Then it's concave up, concave down, concave up. Very straightforward as far as the graph and all the information we need is concerned. The number of bacteria in millions present in a culture at time t in hours is given by n of t equals 2t times 5 minus t squared plus 14t plus 100. find the initial population. By definition, initial population means n of 0, and just plug in t equals 0. This goes to 0, this goes to 0. The answer is 100, what? 100 million bacteria. At what time before 10 hours will the population be maximized? So first and foremost, I'm going to rewrite this as a 10t minus 2t cubed. And I'm gonna put this in descending order by combining these two. And I get negative 2t cubed plus 24t plus 100. And there would be 4 means 10 is not included. So it's half closed, half open. You can think of this as a closed interval theorem. In essence, say this is a polynomial of degree 3. Domain is all real numbers, therefore is continuous from 0 to 10. 10 is not included. And evaluated at the endpoints only one of them, because 0 is included, 10 is not. And then find n prime and set equal to 0 and plug in the critical point. Also, you can do the first or second derivative test. So we have to find n prime anyway. So n prime is minus 6t squared plus 24. Because I want to set this equal to 0, I'm going to factor out the negative 6. Which is negative 6 times t plus 2t minus 2. And when we set this to equal to 0, we get two answers, positive, negative 2, and positive is in between, yes. Negative is in between, no. T is equal to 2 only. Again, if you want to go by the closed interval theorem, just plug in and that will do the job. But I want to show you the first as well as the second derivative test. The first derivative test, we have this sign graph as follows. We're going to go from 0 to 10. Why? Because of the limitation that is here. And we're going to put the critical point to be found. There are 2 of them, only one of them is acceptable. Now the test point, you can even use 0 and 10 as a test point, because you want to know what happens to the left and the right of 2. To the left of 2, you plug in 0, clearly makes this one positive, 24 is positive, and then it alternates. Or just plug in to the right 10, or 3 or 4 or 5, anything in between will do the job. And if you plug in 10, this makes it positive 100 times negative is negative 600. With 24, it's still negative. Okay, so negative 576, and it's negative, meaning let's throw in the arrows. Arrow up, arrow down. So the maximum occurs at t equals 2. This would be the first derivative. However, if you don't want to do the sign graph, the second derivative test makes it easier. How? Here's n prime. What is n double prime? Negative 12t. And the second derivative test says, plug in the CP, the critical point, to see whether it's negative or positive. If I plug in the CP2, I get negative. What does it mean? Negative means concave down, looking like that. Concave down gives us max. So the effect of being negative gives us concave down, and it gives us the max. So what is the maximum population? Plug it into the original equation, or this one, makes no difference, whatever is easier. If you go back to the original one, 2 times 2, 5 minus 2 squared plus 14 times 2, it's easy to see this is 4. 5 minus 4 becomes 1, everybody. So this whole thing is 4. And then 28, 32, plus 132 million bacteria. Very straightforward, fairly simple. Questions? We want to sketch the graph of f of x equals x minus 2 to the power of 2/3 plus 1. And we're going to go through the process. First, I want to show you how to graph this using algebra, using pre-calculus, college algebra, you name it. And I'm going to remind you that we did look at this function when we were dealing with the closed interval theorem. So first and foremost, we're going to rewrite this as the cube root of x minus 2 quantity squared plus 1. This is one way to write it. And to graph this using transformation, we're going to start with the basic elementary function that you're supposed to know, y equals cube root of x. The graph looks like this. And the x-intercept is located at 0, 0. It happened to be the y-intercept. Then we're going to go with x minus 2. So y equals cube root of x minus 2, which means this graph moves to the right by 2 units. So I'm going to just write or move to the right by 2 units. So we're going to move this one, shift it to the right by 2 units. The result is that the x-intercept, which was located at 0, 0, now it's located at 2, 0. Now, the next thing is I'm going to square that. Now, what is the effect of squaring? The portion of a function, the blue function, that is above the x-axis gets squared up and it becomes larger. The portion below the x-axis comes up, becomes positive. So notice, the portion above the x-axis gets larger. The portion below the x-axis flips over with respect to the x-axis. But the location of the x-intercept to 0 does not change. So again, the red one is cube root of x, the blue one is cube root of x minus 2, and now the green one, it's cube root of x minus 2 quantity squared. Finally, plus 1. What is the meaning of plus 1? This graph shifts up by 1 unit. So I'm going to write up by 1 unit. So this function, this graph, this green one, goes up by 1. When it goes up by 1, now this, which had the coordinate 2, 0, now has coordinates 2, 1, 2, 1. We are done with transformation. Now let's add calculus. To do calculus, we are going to differentiate in order to find the CPs, the critical points. And to do so, we are going to differentiate f of x using this part, which is 2/3 x minus 2 to the power of 2/3 minus 1, which makes it negative 1/3, times the derivative of the inside, which is 1, and this is a constant, has no bearing. So in order to do the first derivative test, we want to find f prime of x. We are going to rewrite this by taking this down and making it to the power of positive 1/3, which is the cube root. So f prime of x is 2 over 3 cube root of x minus 2. F prime is 0 if the numerator is 0. Since the numerator is any number, doesn't matter 2 or anything else, it can never be 0, so it has no solutions. None. F prime does not exist, or it's undefined, meaning set the denominator equal to 0. As you can see, when you set this one equal to 0, x becomes 2. Let's do the sign graph. We're going to go from negative to positive infinity. This is our x, this is our f prime of x, and we are going to pick up a test point clearly to the left of 2. For example, 0 would be easy to pick, right? TP, I'm going to call it. So we pick 0 here, and let's say 3 here. So if I plug in 0 into f prime of x, see the numerator is always positive 2. 0 makes this negative 2. Cube root of negative is negative. 3 times that is negative. So positive over negative, this would be negative. If I put 3, this is positive. So the sign of the denominator gives us the sign because the numerator is always positive. So we have negative here, positive here. If I throw in the arrows, arrow down, up, that means local minimum occurs at x equals to, that is the meaning of it, everybody. Now, if we plug back into the original function, this one is easier. This is not too bad. 2 makes this 0. So the answer is 1. So local minimum is equal to 1 at 2 comma 1. What about max? We don't have anything. No local max. Where is the function decreasing? Where is the function increasing? It's increasing here from 2 to infinity. Is decreasing here because we have a negative sign from negative infinity to 2. Now let's go with the inflection points. Possible inflection points, we can find it through finding f double prime. So we go back to f prime, and we want to differentiate it again to find f double prime, and we're going to use this one instead of this, which is an easy differentiation. As you recall, 2/3 times negative 1/3. The product is negative 2 over 9. X minus 2 to the power of minus 1/3 minus 1, which makes it minus 4/3, times the derivative of the inside, which is 1. So minus 2 over 9, the product of these two numbers. X minus 2 to the power of minus 4/3. We're going to take this down again, make it positive 4/3, or a cube root to the power of 4. Notice what's happening with f double prime. The numerator is always negative. What is the denominator? At x equals 2 is undefined. But besides 2, whatever you choose here, whether it's positive or negative makes no difference. The exponent 4 makes it positive. Times 9, it keeps it positive. So the numerator is always negative. The denominator is always positive. The result is negative except at x equals 2. Therefore, it makes the function always concave down. However, not at 2. So how do you write it? You can't write from negative to positive infinity. You have to write From negative infinity to 2, union 2 to infinity, it's concave down because it's negative. And you don't have to do the sign graph. But just in case you didn't notice that, if you do the sign graph, how does it work? F double prime is 0. There is no solution because the numerator is a number. F double prime doesn't exist. The denominator equal to 0 at x equals 2. And you do the sign graph. And again, to the left of 2, an easy point, remember, was 0 and then 3 here. If you plug in 0 here and plug it in here, becomes negative. Cube root is negative. The power of 4 is positive. Denominator is positive. Negative 2 over that makes it negative. To the right of 2, the denominator remains positive. Negative over positive makes it negative. So that gives you the same result in case you don't see the easy way out. So this was the function using the cube root. This is increasing from 2 to infinity, decreasing from negative infinity to 2, concave down. From negative infinity to 2, union 2 to infinity. Here's the minimum. This is all the information we have gathered so far. In order to graph this, we're going to add intercepts. So when we find intercepts, number one, an easy way, set x equal to 0. So if I set x equal to 0, I get minus 2 here. Square it, I get positive 4. Cube root of 4 plus 1. That's a precise answer. However, using a calculator, about 2.6, that's for the sake of graphing when we want to graph. So y-intercept is easy. What about x-intercept? We don't have any. How do we know that? Let's justify that. In order to find x-intercept, you set y or f of x equal to 0. To set this equal to 0, we're going to move the 1. So x minus 2 to the power of 2/3 equal to negative 1. When you have a format like this you want to solve, first you get rid of the denominator by raising both sides to the power of the denominator. So the left side becomes x minus 2 squared, and the right side minus 1 cubed is negative 1. Left side, an expression being raised to the power of 2 is either positive, worst case scenario is 0, can never, ever be negative. Doesn't matter, it's negative 1 or any other negative number. Therefore, this has no solutions. Now we want to sketch the graph. We are going to use the points that we have. One of them is the y-intercept that we have. One of them is the minimum located at 2, 1. So that would be a good idea to write a few more points. How do you come up with easy points? If you go back to the original function, for example, if I choose x equals 1, that's easy. 1 minus 2 makes it negative 1. Cube root makes it negative 1 squared. Positive 1 and 1 makes it 2. I'm assuming nobody has any problem evaluating easy numbers. Another easy number, if I put 3, I get 3 minus 2, 1. Cube root is 1. Squared is 1 and 1 is 2. And you can pick a few more points. Negative 6 is not too bad because makes it negative 8. Cube root is negative 2. Square root 4 and 1 is 5. The same thing happens with 10. 10 minus 2, 8. Cube root is 2. Square root 4 and 1 is 5. But what about negative 1? You need a calculator. So let's plot the pairs. To plot this one, I'm going to go with 2.6. Remember, this is 0 to 5, this is 0 to 5. So it's about 2.6. So 1, 2, 3, somewhere between 2 and 3. And that's my y-intercept. Again, it's pretty close. Then we have 1, 2. So this is 1, 2. 2, 1. This is 2, 1. 3, 2. So this is 3, 2. Which is, by the way, 2, 1 is the minimum. Okay. And then negative 1, 3.08. Negative 6, 5. 10, 5. Putting them together. So what do we notice? A couple of things. Number one, this minimum is not only a local minimum, it is also an absolute minimum equals 1 at this pair. Number two, we notice the function is decreasing from negative infinity to 2, increasing from 2 to infinity. We also notice that the function, the graph of the function is concave down from negative infinity to 2, union 2 to infinity. But we do not have an inflection point.